Honors Pre-Calculus. Welcome to lesson 1.4, Transformations of Functions. Today what we're going to do is distinguish the different types of parent graphs by shape. You will be able to sketch graphs using transformation rules, and you will write equations using transformation form. The essential question today is, how do you apply the rules of transformations to write and graph new functions from known parent functions? So here are our notes for the day, and if you're writing this on your own paper, just do a rough sketch of each of these graphs as we go, all right? So the first thing we're gonna do is name each equation and, write the name and equation. So we're gonna write the name of the graph and the equation of the parent graph. So this first one, it's just a straight line, right? So this is a linear function. And the graph is f of x equals x. The second one, it's a v made from straight lines. That's an absolute value function. With the graph of f of x equals absolute value of x. The third one, a u parabola curve. It's a quadratic function. F of x equals x squared. We'll keep going. The next one is only in the first quadrant. It's curved kind of downwards as it goes up. And this is called a square root function. And the equation is f of x equals the square root of x. The next one is a cubic function, which, as you may guess, has an equation of f of x equals x cubed. The next one has two pieces and two asymptotes, and that is called the reciprocal function, because it has an equation of 1 over x. Reciprocal, remember, means a flipped fraction. And so think of just this as being the flipped version of the original linear function. And our last one might be brand new to you. This is commonly called the step function, or the greatest integer function. And this is kind of unusual. We don't see it that often, but to write this equation, it's f of x equals, and the notation is to use two brackets like this. So it's like double bracket of x, all right? Now, since that is brand new, we're gonna be looking at that first. And up next in the notes is descriptions of all the transformations. We're gonna come back to that when we get to the transformation question. So let's take a look at example 1, all about this greatest integer function. The greatest integer function is defined as f of x equals a double bracket of x. And in words, what it means is the greatest integer less than or equal to x. And I want to show this to you. My calculator is still in my bag, so I'm going to pause for 1 second to go grab it. All right, got my calculator, so I wanted to show you where to find this if you want to graph this on your graphing calculator. If you go to y equals, you're going to press math, go over to the num tab, and it's number 5, int. That's the nickname for the greatest integer function on your calculator. So I'm just going to put x in there, close the parenthesis, and press graph, and you will see the steps, right? Okay, so let's talk a little bit more about what this description means. The greatest integer less than or equal to x. So picture that we're plugging a number in here. So for example, any number between 1 and 2, so maybe 1.5, if you can imagine right where my pen is pointing. We're plugging in 1.5 for x. We're looking for the greatest integer, so integer is a positive or a negative whole number, that's less than or equal to that number. So if we're plugging in 1.5, the greatest whole number that's less than 1.5 is 1. So that's why there's this straight line with a y value of 1 here, because any number between 1 and 2, when we plug that in, is going to have an output of 1. Any number between 1 and 2, the greatest integer that's less than that is 1. And that's going to be true for between every 2 integers on the x-axis. The y value is going to be the same. So it forms these steps, okay? So let's try some of these questions in example A here to see if we can figure this out. So for example, f of -1 is going to be sketched like this, a double bracket of -1. And we are looking for the greatest integer that's less than or equal to -1. Now, -1 is already an integer, right? Integer is positive or negative whole numbers. So the greatest integer that's less than or equal to -1 is -1, right? We don't have to change it at all. If we do -1/2, we think, okay, what's the greatest integer that's less than or equal to x? You know what? Sometimes when I'm teaching this on a whiteboard, I like to draw a number line. So I'm going to do that right now. I just thought of that. And all of the numbers that I'm writing are integers. Okay? And if we think about where is -1/2 on this number line, it's right here. And we want the greatest integer that's less than that. So it's going to be -1. We're also going to try 1/10 and 1.5. 1/10 is somewhere around here. The greatest integer less than that would be 0. And 1.5 is right here. The greatest integer less than that would be 1. In other words, we always round down no matter what the decimal is. Round down. Okay, letter B, evaluate the function f of x equals greatest integer function of x plus 1 when x equals -1, 2, and 3/2. Okay, so I'm just going to start by writing those 3 expressions out. Okay, and the first 2 are pretty simple because they're already integers, so they don't change at all. And the third one here, 3/2, that's 1.5. I feel like we've seen this already. That rounds down to 1. So the last one is 2. So we get 0, 3, and 2 for our answers there. And that is the greatest integer function. All right, a little weird. Maybe you've never seen it, but now you have. We are now going to move into some transformations. So I'm going to flip back to that part of the definitions. And our first section is all about rigid transformations. And all of our transformations are going to have this function notation, which is going to come up later on. So that might be something different, but I think it will make sense. So if we're given that y equals f of x and c is a positive real number, a vertical shift, if we're shifting up or down, looks like this. So if, for example, our function was x cubed, x cubed plus c might be like x cubed plus 4, whatever the c is, I don't know. If we're shifting down, it's going to be x cubed minus 4. Shifting left or right would be a horizontal shift, and that actually occurs within the function, within the parent. So it's wherever the x is, we're adding or subtracting the c. So in this case, it would be x plus 4 cubed or x minus 4 cubed. So wherever the x is, that's where we put the c. All of these shifts so far are rigid transformations. That's an important term to know. Rigid meaning like hard or sturdy, right? So when this shift happens, the shape of the graph is staying exactly the same. It's just shifting. Think of it like a hard object. When we get to the non-rigid transformations, you'll be seeing like stretches and shrinks, and the graphs will actually look different. For now, we're just moving something, but it's staying exactly the same shape. Even if it's reflecting, it still counts as a rigid transformation because it's not changing shape, potentially just the direction. So a reflection in the x-axis has a negative in front, and a reflection in the y-axis has a negative inside, like that. Now, you may be looking at this and thinking, wait a second, if we do negative x and we cube it, we get negative x cubed. That's true, and if you think about the x cubed graph, a reflection over the x-axis or a reflection over the y-axis are actually exactly the same. Either this flips over here or this flips here, and they're going to look the same either way. So that's an interesting phenomenon that's going on there. So that's our reflections. And next up, we have our non-rigid transformations. So we can have vertical stretches and shrinks and horizontal stretches and shrinks. And it's all about a number multiplied either in front or inside of our parent. So if we look at that x cubed again, it would be something like 4x cubed. Or if we're going to have a vertical shrink, the number has to be between 0 and 1. So maybe it's like 1/4 x cubed. Same thing for horizontal, but it's inside. So this one might be like 1/4 x cubed, and this one could be 4x cubed, like that. Okay, so that's a little overview of our transformations. A vertical stretch is like you're pulling it vertically. A vertical shrink is you're squishing it vertically. Horizontal stretch goes this way. Horizontal shrink goes this way. All right, so that is that. Now we're going to move into example 2. Describe the transformations in the following functions given the parent function of x cubed. That's what we were just looking at. So in this first one, there's only one extra thing, the -1 at the end. And if you're following along so far, that means that we're shifted 1 unit down. In letter B here, we have two things. We have this +2 and we have this +1. The +2 means we're shifted 2 units left. And the +1 means we're shifted 1 unit up. So the whole graph is shifted to the left and up. Example 3. So now we're going to see some visuals here. Given the graph of x to the 4th below, use visual transformations to find the equation for each graph. All right, so in letter A, what I want you to notice is the vertex is moved from 0, 0 to 0, 2. So we are shifted up 2. And we are also reflected over the x-axis. As you can see, instead of curving up, think of this as the x-axis. We reflected over it, so now we're curving down, and then we shifted up 2 units. So that graph is, I'm just going to call it g of x. If the initial was x to the 4th, we have to reflect, so it's a negative x to the 4th. And then we have to go up 2, so it's +2 after. Okay? In letter B, it's also reflected in the x-axis. And this time we're shifted to the right 3 units. As you can tell by the vertex again. So this graph, I'll just call it h of x, is going to be negative. And since we're shifted right, the -3 has to be inside before we, oops, I wrote cubed, but it's to the 4th. Before we make it to the 4th. So there's the equation for that one. All right, that brings us to example 4. Reflections and shifts. Compare the graph of each function with the graph of the parent function f of x equals the square root of x. So this time, in letter A, we only have one thing changed, and it's a reflection in the x-axis. But if the negative's inside instead, it's a reflection in the y-axis. And in this third one, we have two things going on. The first is a repeat. It's a reflection over the x-axis. And the second one, that's +2, means that we're shifting 2 units left. Okay? Example 5, non-rigid transformations. Compare the graph of each function with the graph of the parent function. Okay, so this time we have the absolute value of x, and we're looking at non-rigid. So these ones are going to stretch or shrink potentially. So if we have a 3 in front, that is greater than 1. So this is considered a vertical stretch. And I would say it's by a factor of 3. Basically, everything's being multiplied by 3, which you can tell because everything is being multiplied by 3. And over here, since we're multiplying by a third, it's going to shrink everything. So this is a vertical shrink by a factor of 1/3. Okay? And that brings us to example 6, our last example for the day. If f of x equals 2 minus x cubed, find the requested equation and describe any transformations. So g of x equals 2 minus x cubed, or f of x equals 2 minus x cubed. G of x equals f of 2x. So g of x is the same as f of x, except wherever there was an x, now we're substituting in 2x. So this x is being replaced, right? Because if you look at the initial was f of x, now it's f of 2x, so we're replacing x with 2x. So it's going to be 2 minus 2x cubed. And if we compare this with this, which technically here is like our parent, it didn't necessarily say describe the transformations based off of a parent graph. It just means transformations between this and this. So the only thing that changed, this 2 in here, means that this is a horizontal shrink. If you go back and look at our rules, and it's by a factor of 2. And in letter B, f of 1/2 x, g of x equals 2 minus 1/2 x cubed. And that's multiplying by something between 0 and 1, so this is technically a horizontal stretch by a factor of 1/2. All right, so those last ones are a little bit weirder, but I think this will make a lot of sense to you when you look at the worksheet. If you have any questions, let me know. Thank you very much for watching.